In today's video, I'm going to talk about mesh analysis, nodal analysis, superposition analysis, Thevenin Equivalent Circuit. So this is a method we use to do the circuit analysis on DC circuit. And all the method works on the pure resistance circuit. When I say pure resistance, that means we have the power source and also the resistance, nothing else. So the power source could be the voltage source, could also be the current source, and the other thing is the resistor itself. Now let's look at one example. So it's about mesh analysis. So let's say we have a circuit like this. We have three power source, E1, E2, E3. We also have three resistors, R1, R2, R3. So by looking at the circuit, we have two loops here, loop 1 and loop 2. So we need to build two loop functions by using KCL. So the first loop is we have I1 goes through R1. So this is used power. And therefore we have another resistor, R3. So for R3, we have I1 goes down, we have I2 goes up. So the total current for this one will be I1 minus I2 times R3. So we have two power sources, E1 and E2. So the total power will be E1 plus E2 because they have the same direction. So this is our loop 1 equation. Now by looking at the second loop, so we have the power source E2 and E3 and they have different direction. So for the power use, if we use this as a positive direction like I2, so that will be I2 minus I1 because they have different direction times R3, then plus I2 times R2 equal to the total power here. That will be E3 minus E2. So this is our loop 2 equation. Now we just need to plug in the numbers in order to get the current. So we have I1 times R1 is 200, then plus I1 minus I2 times R3 is 600. That equal to 12 volts plus 3 volts. So here the first one will have 800 I1 minus 600 I2 equal to 15. So this is our loop 1 equation. For loop 2, it's I2 minus I1 times R3 is 600. Then we plus I2 times R2. R2 is 100. And equal to E3 is 18 minus 3. So the total will be 700 I2 minus 600 I1 equal to 15. Now we just need to connect these two equations in order to solve for I1 and I2. So 800 I1 minus 600 I2 equal to 15. Then 700 I2 minus 600 I1 equal to 15. So by using math, we can get I1 equals 97.5 milliamps and I2 equals 105 milliamps. So for the total current I, for the R3, since they haven't, I is here this direction, I1 is also this direction, but I2 is this direction. So I will be I1 minus I2 because I direction is the same as I1, so we put I1 first and minus I2. So that will be 97.5 milliamps minus 105 milliamps. That will give us minus 7.5 milliamps. So minus sign means the direction is different. From I1. So that will be the same as I2. So for the current I direction will be this direction goes up, same as I2. So this is how we use mesh analysis to do the circuit analysis. So we determine how many loops do we need, so loops. Then we just kind of define our i's, I1, I2, based on how many loops. If we have 2 loops, that means we need to solve for 2 current. If we have 3 loops, we need to solve 3 current. Then after we get the current for each loop, we can get the total current that flow R3. But we need to be careful about the directions of the current. So we define the current for R3 is going down. So we define the R3 current is going downward. So it will be same as I1, but it will be different for I2. So the total current I will be I1 minus I2. If we get minus sign for the result, that means the direction is different from what we defined. That would be go upwards. Now let's look at the second example here. Let's say we have a circuit. So this is one power source here. We have the load resistor here. We have another resistor, another power source. So R1 equals 8 ohms. R2 equals 4 ohms. And R3 equals 10 ohms. E1 is 24 volts. E2 is 5 volts. So the current I is this direction. So we need to do the nodal analysis for this circuit in order to find the current I. So for the nodal analysis, we need to convert the voltage source to current source. So for this one, it will be, the current will be E1, I1 equals E1 divided by R1. So it's 24 volts divided by 8 ohms. That will be 3 amps. For I2, it will be E2 divided by R3. That will be 5 volts divided by 10 ohms. That will be 0.5 amps. Now we have 2 current source. So for I1, it will goes up. It's the same direction for the positive side power source. So we have I1. So this is A1. We have resistor R1 now. We have second one R2. We have third one R3. And we have another current source, A2, that goes down. This one goes up. So this will be R1, this will be R2, this will be R3. This is the ground. So this will be node. So let's say this is V1. Right now we have, if we use K, so for the mesh analysis or loop analysis, that will be KVL, not KCL, the Kirchhoff voltage law, not the Kirchhoff current law. So here that will be KCL. So for A1, it goes from here, then this is our I. This is I1, this is I. This will be not I1 anymore. It will be I11, I12. So for current I, it will go to this one, this one, this one, this one. So I1 will equal to V1 divided by R1 plus V1 divided by R2 plus V1 divided by R3 and plus I2. So from here, we can solve for V1. So basically, I1 will equal to, if we pull out V, that will be 1 over R1 plus 1 over R2 plus 1 over R3 and plus I2. These three in parallel. So that's V1 times R1, R2, R3 And the first one will be R2, R3. Second one will be R1, R3. Third one will be R1, R2. Then plus I2. Then we have V1. After we plug in the numbers, so R2, R3 will be 4 times 10 plus R1, R3, 8 times 10. Then plus R1, R2, 4 times 8. Then divided by 4 times 8 times 10 plus I2. That'll be V1 times 0.0475, then plus I2. So V1 will be I1 minus I2 divided by 0.475. That will give us 3 minus 0.5 divided by 0.475. That will be 5.26 volts. Then we can solve for I. It will be V1 divided by R2. So we have 5.26 volts divided by R2 is 4 ohms. That will give us 1.315 amps. So this is how we do the nodal analysis. So first we need to convert the voltage source to current source. Then all the resistors are in parallel. Then we use KCL, the Kirchhoff current law. So the total current I equals the current flow for this one, and also this one. After we build the equation, we can solve for V. After we get V, we can get the current for this branch. It's going down. We can get the current for this one. We can even get the current for this one. Now let's look at another example for superposition theorem. Let's see if we have a circuit like this. We have a current source. Goes up 3 amps. We have one resistor here. We have another resistor here. We have the voltage source here. So the current goes this direction. V1 equal to 18 volts. And R2 is 30 ohms. We have R1 60 ohms. So we need to solve for I. So for the superposition theorem, we need to replace the current source with the open circuit. So basically we need to remove the current source and we need to replace the voltage source with the short circuit. So step 1, we replace the current source with the open circuit. Then after that we will have, so that's open here. We have one resistor here, R1 60 ohms. We have R2 equals 30 ohms. Then we have the voltage source here. This would be the ground. So E equal to, or V1 equal to 18 volts. So basically we only have one series circuit. This is Ri. So the current will be I equals I1 equal to 18 volts divided by R1 plus R2. That will be 18 volts divided by 30 ohms plus 60 ohms. That will be 0.2 amps. Then step 2 is replace the voltage source with a short circuit. That will have one current source here, goes up. Then we have one resistor here, we have another resistor here. So that will be a short for E. Now we have R1, R2. R1 is 60 ohms. R2 is 30 ohms. So we have a current goes this direction. So basically R1 and R2 in parallel. And then we have the current here, so we can use current divider. So I2 will be equal to I times R2 divided by R1 plus R2. Then it will be 3 amps times 30 ohms divided by 60 ohms plus 30 ohms. That will give us 1 amps. So the total current for I, since they go to the same direction, that will be I1 plus I2 for the total. So that would be 0.2 amps plus 1 amps. That will give us 1.2 amps. So this is how we do the superposition theorem. We replace the current source with the open circuit. We replace the voltage source with the short circuit. Then we find the current separately. So if we replace the current source with the open, we have a series circuit R1 and R2. So the voltage is 18 volts. The current will be I equal to 18 divided by the total resistance. That will give us 0.2 amps. Then we replace the voltage source with the short circuit. Then we have R1 and R2 in parallel. Then we can use the current divider to find I2. So I2 will be I times R over R1 plus R2. Then opposite, since we have the same direction, both currents are going down. So I1 is going down and I2 is also going down. So I will be the I1 plus I2. And the direction is also going down. Now let's look at our last example for the Thevenin equivalent circuit. So let's say if we have a circuit like this, have one resistor here. This is our load, and then we have another resistor here. We have another power source. So this is E1 equals 24 volts, and E2 equals 6 volts. R3 is 12 ohms. Our load is, this is A, this is B. We have R1 equals 8 ohms. So we need to find the equivalent circuit for this guy. So basically we need to convert the ETH and RTH. So in order to find the RTH, we need to remove the load and also replace the voltage source with the short. So if we replace the voltage source with short, so we will have R1. And we have a short here. And we remove the load. That's an open circuit here. Then we replace the E2 with a short. This is R3. It's a short here. This will be RTH. So basically RTH is R1, R3 in parallel. So RTH will be R1 times R3 divided by R1 plus R3. That will give us 8 times 12 divided by 8 plus 12. That's 4.8 ohms. And for ETH, we need to put the power source back. This is R1. Remove the load. This is our load. This is R3. This is another power source. So this will be ETH, like we put a voltmeter here. What's the voltage here? So this is R1, this is E1, 24 volts. This is the E2 equals 6 volts. So basically we have a series circuit and we need to find the current for this circuit. So this is our ground. So in this circuit, the current will be, by using KVL, we can build loop. So that will be E1 minus I times R1 minus I times R3. And we need plus E2. That will be 0. Since the power sources have the same direction, so that will be E1 plus E2. So the current I will be E1 plus E2 divided by R1 plus R3. That will be 1.5 amps. Then we can find the voltage drop for R3 since the current goes this direction. This is I, so this is I. So V3 will be I times R3. So that will be 1.5 amps times R3 is 12 ohms. That will be 18 volts. So ETH, if we look at this loop, that will be V3 minus E2. So that will be 18 volts minus 6 volts. That will give us 12 volts. So this is ETH. So the equivalent circuit, it will be this. So the positive direction will be the same as the bigger voltage source. Then we have ETH. We have RTH here. So this is our equivalent circuit. Then we'll have RL here. This is our load. So this is how we convert the circuit to Sin's equivalent circuit. So first we need to find the RTH by replace the power source with a short and remove the load. Then these two resistors are in parallel. Then we need to calculate the parallel resistance. After that, we remove the load and put the power source back. Then we have one loop here. This is our zero reference. So there's only one loop here, so we can find the current. After we find the current, we can find the voltage drop for R3. Then we can find just ETH by using KVL. If we just look at this loop. And we can also determine the direction for ETH, the positive side. So that would be basically the ETH will be the same as E1, the positive side, because E1 is bigger than E2. Then after that, we can redraw the circuit to the Sin's equivalent circuit, something like this. Okay, that's everything for today's video. Thank you for watching.